Hi everybody, welcome to week 2 in GIST. We're going to be looking at chapter 2, goes well with week 2. And the study of this week is quite literally the basis for everything we do in mapping and in using GIS technology effectively. The chapter title asks, where in the geospatial world are you? Which means is, how do we know how to locate those things, places, and phenomenon that we talked about in chapter 1 and place them on the world, on the earth, or on a flat map? You might be familiar with concepts such as coordinates and maybe even map projections. But the question is, how did we get those? Where do these numbers and map shapes come from? And what impact can they have on the accuracy of our mapped and represented data? For today, we will review how we get from the real Earth that we're standing on to the flat maps that we see in books, classrooms, and on the internet. And my goal will be to have a better understanding of what is meant by projections, coordinate systems, and datums, and how they impact your use of GIS technology and any mapping project you embark on. And before we get started, let me just add and reiterate, like so many things we're going to study, this is a science in and of to itself. There are a set of very clever scientists called geodesists. They study geodesy, and they're very talented mathematicians, and they look exclusively at how the Earth, the math behind and the geometry behind looking at circles and ellipsoids, which we'll get into more in detail in just a moment. So if some of the concepts seem a bit tough to wrap your brain around, don't worry. You can always have these, like for instance, this PowerPoint to come back to and reference, but it's complicated, and it takes me a long time. It took me a long time to sort of really grasp what's going on. So with further ado, I will turn myself off and we can move on to the slideshow. So knowing where you really are on the Earth is a lot harder than it seems. If you look at the landscape around you, I'm sure you see mountains, valleys, or even vast stretches of plains and hills. And you know that even in areas where there are plains and hills, some areas are at higher elevation than other areas. So when we talk about precision, we have to take these things into account. But is it really possible? Is it possible to be that precise, given that we can't really know where we are? Well, yes and no. I mean, we can find out where we are using our sophisticated GIS technology, our elevation, our coordinates, etc. And like in the image here, where we have XY coordinates, and we even have a vertical coordinate. These locations, these coordinates, these numbers are only useful in relation to a reference system. So we have to know in what context they're being used. This is sort of meaningless unless it has reference. So as we're going from this real Earth to this flat map, what we're really building is an understanding of what reference system we're using and that we're depending on for our mapping. So because the Earth's surface is not flat or evenly distributed, our measurements can never be absolutely perfect, though we can get darn close. And we can do this because those geodesists I mentioned have figured out how to most accurately represent the Earth, according to our mapping needs, I must add, allowing us to create meaningful geospatial data. Before we move on to the next slide, I just want to point out the video here at the bottom of the page. I actually have it posted on the course page for this week. But it's about 8 minutes long, but it's a good another way of learning the jargon and all the kind of vocabulary you will be exposed to today and in this chapter. So here's our first mind-bending concept, I think. So while you may know and accept that the Earth isn't perfectly smooth, did you know it's actually quite squat? So it has this big center in the middle of it. The shape you see here is called a geoid, and when talking about the Earth's real shape, this is what it looks like. Because of the long-term effects of gravitational pull on the Earth at the equator, and a good way to think about that is like if you have your arms loose by your side and you spin around in a circle, your arms will gently lift outwards. That's kind of the same thing. Your arms are pulled out and creates what's called a geoidal bulge, which I think is a very funny way to say that you've actually put on some weight. We also can't forget about our friend the ocean. If you've ever tried walking with a bowl full of water without spilling it, you know that it gently sloshes side to side as you move with the bowl. So if there were no tides and currents, this hypothetical ocean would just gently undulate, and this is what would happen to the oceans as the planet spins. So when you take this undulating tide-free ocean along with the geoidal bulge and the general lumpy topography, we have our geoid, which is also known as a lumpy potato. The image you see here is based on a computer animated rendering of the geoid based on remote sensing imagery taken in 2011. You can see the link on the slide below. It's actually really fascinating because they used low orbit satellites to take all the readings to construct the image you see. Okay, so remember, we're moving through how to get from the real Earth to a flat map. The geoid we learned about in the last slide, that's our real Earth, full of inconsistent features and undulating oceans. If we smooth that geoid out, but keep the bulge, we are left with an ellipsoid, as seen in the lower right, over here. The ellipsoid is good because it smooths out all those lumpy features, but it's still not easy to make calculations based upon its shape. So we tweak it a bit to get the spheroid you see in the bottom left. So you notice how the three axes have the same value in the spheroid as opposed to the ellipsoid. This is important because it then makes applying geometric calculations to the Earth's shape a little less complex. So what's happening is we're approximating the geoid using a regular shape. We're kind of generalizing that irregular surface with something that's smooth and easier to calculate. So now that we've created our spheroid, we've generalized that surface, we can use that to further create the reference surface. We're going to start getting into our reference surfaces now for the Earth. That's called the datum. So the datum is created by establishing an average of Earth's uneven surface, like we already discussed, superimposing a smooth spheroid over that lumpy potato. That's a bit of a tongue twister. It wouldn't fit perfectly, but it would approximate the roundness of the geoid. In reality, geodesists need to know points with highly accurate known locations to create a datum. And in the United States, you may have come across these markers here. They are used by the National Geodetic Survey to establish the known points needed to create the North American datum. And these points are then used to create a mathematical model of the spheroid cone datum that best represents where you are mapping, in this case, North America, with this Geodetic Survey marker. And I've mentioned this a few times already, that the datum is created for a specific mapping purpose, and I'll get into that a little bit more in a moment. But we can just see here again how this is approximating the roundness. It's averaging it out, so we're taking our highs and our lows, and we're getting the best fit, even though not everything will fit inside of it. And that leads into types of datum. There are many types of datums based on differing measurements and mapping needs. Whatever datum is being used represents a sort of average of the Earth's uneven surface, but it also depends and differs on what you are trying to map. So looking at this slide, we see two different ellipses, the red and the yellow, and they have different mass centers. The mass centers aren't so important other than just to say keep your eye focused on where the size of the circle, really, the size of the ellipse. So these ellipses actually represent different kinds of maps. The yellow ellipse is larger and is trying to account for the Earth's surface as a whole, which we will call the global datum. So this is what we would use if we were mapping the whole Earth, if we were trying to get from a whole real Earth representation to a flat map of the whole Earth. This is as opposed to this red circle, this red ellipse, which you'll see is kind of pulled in tightly on this lower section down here. I'm going to pretend that this is focusing on Australia, because that's kind of where Australia would be. So as you can see, our ellipse became smaller, and that means it's capturing a lot more detail down here in Australia. So that also means, the implication is that if we had the Australian datum, we were using that for a mapping project, and we decided to map something over here in North America, it wouldn't work. It wouldn't fit, and we'll see a little bit more of that in a minute. So just know that there are different kinds of datums out there. So here's an example of some of those datums. The first one we see here is from 1830, and then we come all the way to our current ones, and you can see there's different users. So these, again, are going to have those different levels of accuracy depending on who's using it and what mapping you're doing, what your purpose is. It's amazing to think that people were doing that kind of complicated math so long ago before computers. So why is this all important? I'm sorry, let's look a little more closely at the differences between types of datums. There's the local versus the global. Here we see two different datums for North America, one from 1927, and hence it's called NAD 27, which sort of sounds silly, but it stands for North American Datum 1927, and another one calculated in 1983, also shorthand is always called NAD 83. Simply put, the local datum uses a center point for the region that's being mapped on the ground, so it's on a flat surface. And in this case, for this NAD 27, the center point is in Meads, Kansas, which is actually the 00 coordinate for this North American datum. There's actually some very interesting stories attached to this location because many computer systems use this 00 as a location, a geospatial locational default. And I won't give away the fun stories, but I've posted the link on the course page. I think you might find it interesting. This is in comparison to the global datum, NAD 83, which is conceptualized based upon more like the three-dimensional sphere that we've been dealing with so far. So again, it fits into it's that Australian red circle datum we saw on the last slide. It's fitting much closer against the North American continent. So the center of the sphere is in the Earth, and that kind of changes the way we do the calculations in the satellite mathematics and readings. Why is this also important? Well, it has everything to do with accuracy. Remember that reference system we discussed a few slides ago. If you don't know what my context is when I say I have a date, you could think I mean a fruit, that I'm going to see a movie with someone special, or I have something on a calendar. In the same vein, when you have coordinates or some kind of geospatial data, unless you know what datum it was created using, the points or the shape of the things will not line up. In this example, you can see the variance on a trail map between two different datums. It is quite different. In this example, there's probably about 200 to 300 feet off, which can be really detrimental. In a GIS, we can actually convert the mapping done on different datums. This is called transformation, so that it matches, but it is still important to know that the datum used is fundamental to the accuracy of the geospatial data. Okay, so now we're ready to keep moving along that path from the real Earth to the flat map. And so far we've covered the geoid, the spheroid / ellipsoid, and the datum. Now we're going to divide that datum up into a bunch of intersecting lines to create something I'm sure you've all heard of, longitude and latitude. Now this is also known as the geographic coordinate system. Coordinates in a geographic coordinate system are read in degrees, minutes, and seconds, though there's also decimal degrees as well. So let's talk a little bit more about latitude and longitude and ways to numerically represent coordinates. Just to sort of remember some of the vocabulary here. A meridian is longitude. It runs from north to south, from 0 to 180 degrees east and west of the prime meridian. And famous meridians include the prime meridian and the anti-meridian, AM and PM. A parallel is a latitude. It runs from east to west and from 0 to 90 degrees north and south of the equator. Famous parallels include the Tropic of Cancer and the all-famous equator. And I mentioned before the degrees, minutes, seconds versus decimal degrees. What's the big difference? Well, really none. It is actually personal preference. You will always find your intended point as long as you're using the intended datum. Some people find degrees, minutes, seconds easier to handle or think about because the coordinate is an understandable circle or sphere, which we know is divided into 360 degrees or chunks of 360 degrees, and thus is just easier to think about. But on the other hand, they can get unwieldy and long, and you can see in this example here, this is where Easter Island is. So on the degrees, minutes, seconds, it's quite long, as opposed to the other example. It's a little shorter and more easier to handle. Okay, so continuing along the path of going from that real Earth to the flat map, we're going to make the final leap to map projections and projected coordinate systems. So this is projecting your 3D geographic coordinate system, or your three-dimensional sphere, onto a 2D surface. So to define your projected coordinate system, you need a datum, which we talked about, and you need your map projection. So how do we create projections? Recall that with the geographic coordinate system, we are dealing with location on a three-dimensional object, the spheroid or ellipsoid that represents the Earth. So how do we get from this to the projected map? Well, let's do a quick thought experiment. That's kind of illustrated here in the slide. Imagine you have a clear plastic ball with the outline of all the continents and latitude and longitude drawn onto it with a dark black Sharpie. You also happen to have a light bulb in the center of that ball that you can turn off and on with a switch. Third, you have a piece of paper wrapped around the ball like a cylinder, touching the ball only along one narrow strip. In this example it doesn't, but imagine it being tightly folded up against the ball and just one, like along the equator. If you turn on the light bulb, take your marker and trace an outline of what is shown onto that piece of paper, and then you take it off, unwrap it, and lay it down flat, you have your projected map. Ta-da! So when you examine the map, you might notice that there are distortions in the shape of the continents. If you repeat this projection experiment with a few different times with the paper wrapped around the spheroid at different angles and places on the ball, you'll notice that the distortions change. And this is how we get different kinds of map projections, some of which you may have heard of, such as Mercator and Robinson. It is important to remember that all flat maps have distortions of one kind or another. There's no single projection that truly shows an accurate flat Earth. And here we see the different kinds of paper wrapping, so to speak, or that we can do on a spheroid, and also how it can be oriented on the sphere and intersected. And all of these create different kinds of maps with different purposes. And in terms of the distortions that happen, there will always be some kind of distance, direction, scale, area, or shape distortion. And different projections can be used with different datums. It's just what it comes down to is what your needs are as a mapper and as a cartographer, because there's certain kinds of maps have different purposes. So let's look in a little more detail at how the Mercator projection works. This is one we see very commonly used, but famously distorts the size of Greenland, so to speak. Just to give this context, Greenland, which is incidentally the largest island in the world, is 12th on the list of countries, largest countries by area, at 2,166,086 square kilometers. By comparison, Saudi Arabia, which is just below Greenland on the rankings at number 13, which is down over here, is only 20,000 kilometers smaller. But when you compare these two regions, Greenland looks gigantic. And the reason for the distortion has everything to do with the shape of the paper wrapped around the spheroid used to represent the Earth. So where you see up here, it's long and narrow, or long and open at the top. The projected images stretch up as that light shines through the globe, whereas the stuff that's at the place where the paper is touching the globe has very little to no distortion or stretching. Okay, just briefly I'd like to introduce the Universal Transverse Mercator projection, which is important because it is actually used most commonly with web-based mapping, which we'll be learning about more later this semester. There are many cool things about this projection, but here I just want to point out that projections don't always have to happen kind of in the strict north-south orientation kind of that we see with the traditional Mercator projection. In this case, the paper, the hypothetical paper, is wrapped around the Earth on a north from, I meant east-west in my previous example. The paper is touching from the north-south, and it gives us this sort of rectangular, chopped up look here. But we'll explore that in more detail later on this semester. So now I have an added bonus, a brief introduction to the state plane coordinate system. Ooh. If you continue on in your GIS education, you'll start to see a lot of this. The SPCS is an even more accurate and detailed representation of the geography of each state in the U.S., to the extent that many states have multiple coordinate systems. This is just important to file away in the back of your head as you continue to use more geospatial data that comes from federal and state resources. An important thing to remember is if you ever see something called the FIPS code, FIPS, it stands for Federal Information Processing Standard, and it's one of these codes here. And you'll know what coordinate system it's referencing. And obviously many states have multiple coordinate systems within them. This just means we have even more locally relevant accuracy with our mapping. So to review, let's just look quickly at how we got from our real Earth to our flat map. We started with our geoid, the imperfect lumpy potato, and then we regularized it and averaged it out and created an ellipsoid, which then was manipulated to become the datum. The datum was divided up into latitude and longitude into a geographic coordinate system. And then a three-dimensional sphere with all of its lines had a light bulb stuck in the middle of it and was shown onto a piece of paper and drawn out to create our flat map. And here it is in a few more words. The bottom line is, when making maps, your projected coordinate system, geographic coordinate system, and datums must match, or else geospatial data will not align. And datums are also very important when we're working with GPS, because they're much more generalized, and GPS, because the satellites are floating all over the place, have to have a much more larger regularized reference system. So to end, I highly recommend you watch The West Wing, Season 2, Episode 16, this clip here called the Gauss-Peter projection. It's only about 7 minutes long, but it's very funny, but it's also very enlightening, because what it brings up is something that is very elemental to, is at the bottom line of all of this accuracy and map projections. Because of course, while accuracy is important, the other thing that's happening with all these projections is they have a very sort of political component to them. There's a lot of things that can be hidden or disregarded or sort of talked around on a political level, depending on how you're representing the Earth, so depending on what projection you're using. So check that out, and also you can look at what your favorite map projection says about you. And it's kind of a funny little way to learn a little bit more about these different projections. I'll also have a few more links up on the course page about some really neat map projection animations. So that's it for today. I know it's kind of a really big topic. I hope you kind of got some of the point of it. And as we move along through GIST, I think a lot of this will start to kind of come together a little bit more for you. And with that, I will say goodbye.